All right, hey everyone, welcome back. So this week is our second to last lecture, and it'll be about some trig definitions and identities. So we'll be covering some of the basics at the beginning, closely following the handout, which is as usual posted on our website, and then we'll diverge to competition problems towards the end. And with this one, we highly recommend pulling up the handout since it has a lot of the identities listed out, which will be really helpful in following along. So we'll get started with what trigonometry is. Trigonometry is basically the study of relations between angles and side lengths in triangles. Though in higher levels of math, they can be used for much more complicated applications. And one of the most common ways to define the basic functions is using a right triangle. So we take this right triangle and look at this angle x. We can label the sides as follows. This side would be defined as the opposite side, which we'll just call O for now. This side would be adjacent side, and this side would be hypotenuse. A common mnemonic used in pre-algebra is Sohcahtoa, specifically this. And this is used as a way to figure out what the values are for the three main trig functions, sine, cosine, and tangent. So the first part, the SOH, is for sine. We get that sine of x equals opposite over hypotenuse. Similarly, we get that cosine of x equals adjacent over hypotenuse. And finally, tangent of x equals opposite over adjacent. An interesting property is that tangent is also equal to sine of x divided by cosine of x. So there are also three other less commonly used trig functions, which are the inverses of these functions. We have cosecant of x, which is equal to 1 over sine x, secant of x, which is equal to 1 over cosine of x, and finally cotangent of x, which is equal to 1 over tangent of x. So note that cosecant is paired with sine and secant with cosine, which is somewhat counterintuitive given the name, but after the first time you should be more familiar with them. And we can apply these definitions to some easy angles, specifically in 30, 60, 90 triangles and isosceles right triangles. So let's start with the easiest one, a 45, 45, 90 triangle, which is basically a right triangle where the two sides are equal. So if we call their lengths a, that means the last side has the length of root 2a by the Pythagorean theorem. And both these angles must be 45 degrees since the sum of the angles in a right triangle in any triangle always add up to 90. So now using the definitions of sine, cosine, and tangent that we defined before, we get that sine of 45 degrees equals the opposite side, which is over here, a, divided by the hypotenuse, which is root 2a, which just gives you 1 over root 2, and if you rationalize this, this is equal to root 2 over 2. Similarly, for cosine of 45, it turns out that this is the exact same since both the sides have the exact same length. So cosine of 45 degrees is also root 2 over 2, which means that tangent of 45 degrees is equal to just 1. So with a 30, 60, 90 triangle, it's slightly more complicated, but we can make it by splitting an equilateral triangle in half. So if you remember, an equilateral triangle has all three of the sides have an equal length, and all the angles are 60 degrees. So if we split it in half, this top angle becomes 30 degrees, and this becomes a 90-degree angle. So now once again, using Pythagorean theorem, if this thing has length x, this has length 2x, and this thing has length root 3 over 2x. So we can again use our definitions of sine, cosine, and tangent to get that cosine of 60, which is equal to this side divided by the hypotenuse, also happens to equal sine of 30, which equals 1/2. And similarly, cosine of 30 equals sine of 60 equals square root of 3 over 2. So this actually demonstrates one of the fundamentals of trigonometry, one of the identities which we'll get to later. The sine of 90 minus x is equal to the cosine of x. So they're basically flipped with relation to 90 degrees. So finally, we can also get the value of tangent. So tangent of 60 would equal cosine of 60, sine of 60 divided by cosine of 60, which gives you that It gives you the value of root 3. And similarly, tangent of 30 would give you 1 over root 3, or root 3 over 3. So put together, these are basically just some of the ways to see some of the easier angles. And these three angles specifically, 45, 30, and 60, should all be basically memorized. And even if you don't have them memorized, you can derive them in a similar manner during a competition if needed. So however, at this point, there's a big flaw with the current definition. If we define trigonometry using only the angles of a triangle, we're restricted to angles less than 90 degrees. Since in a right triangle, no angle can be greater than 90 degrees. To get past this, we use an alternate definition called the unit circle. So basically, if we take a circle of radius 1 centered at the origin of the coordinate plane, the value of a point on the circle is this angle away from the x-axis, which we can also call the pole, is cos theta comma sine theta. And if we notice, this works the exact same way in the first quadrant as it did for a triangle. But in the other quadrants, we get negative coordinates, whether it be for the x1, y1, or both. So a common mnemonic device to see which one's positive is that all students take calculus. So that basically means if you go around the quadrants in this direction, we get that all of them are positive in the first quadrant, only sine is positive in the second quadrant, only tangent is positive in the third quadrant, and only cosine is positive in the third quadrant. When I say only, I also mean their inverses would work as well. So cosecant would also be positive in the second quadrant since sine is positive, but the inverses of these trig functions aren't used as often. The unit circle is very useful for seeing a lot of identities that we will cover shortly. And another small point before we move on, all values of sine and cosine, since they're on the circle, must be less than 1 in magnitude, which is very useful for a lot of inequalities in bounding. Next, we'll move on to some of the most common identities in trigonometry. And we'll start with the shifting identities, which basically means that we shift our angle by a nice value or just take the negative of the angle. We've provided the whole chart here, and while it definitely is complicated, it's not that bad to memorize if you utilize the unit circle. For example, sine of negative x equals negative sine of x. If we draw out the unit circle, we can trace x degrees above the pole and x degrees below the pole. Both these points are inline vertically, or inline horizontally, but are on opposite sides of the x-axis. This means that the value of this point's y coordinate is the negative of this point. So if we convert it back into sine and cosine, we just get that sine of x equals negative of sine of negative x. And that basically gives us our trig identity right here. We can also similarly do this for cosine. Both these points are sine of x and sine of both these points are x degrees above and x degrees below, which is positive x and negative x, but they have the exact same x coordinate. And since the x coordinate defines the cosine value, that means that we have that cosine x equals cosine of negative x. So in the same manner, we can derive most of the first column pretty easily. On the other hand, we have shifts by pi, where we would find ourselves on the opposite side of the circle. So once again, if we draw a unit circle, and we have some angle here, if we shift by 180 degrees, that would take us all the way to the exact opposite side of the circle. So the coordinates would in fact become negative of what they were, which means that cosine of 180 plus x equals negative cosine x, and sine of 180 plus x equals negative sine of x. A quick note, in this chart we use the radian measures, which are basically the same as degree measures, except pi radians are equal to 180 degrees. In actual calculations, it doesn't make too much of a difference as long as you just don't get mixed up whether you're using radians or degrees. So one thing to notice from this, if we actually take tan of 180 plus x, we get that this is equal to sine of 180 plus x divided by cosine of 180 plus x. But using what we just found over here, this is just equal to negative sine over negative cosine of x equals just tangent of x. So tangent, in fact, just repeats every 180 degrees, unlike cosine and sine, which repeat every full revolution. So finally, the other types of shifts are shifting by 290 minus x and 180 minus x. So we can see this again on the unit circle. If we take a point over here and shift it to 90 minus x, it would basically be reflected across the y-axis. So basically, this wouldn't change the y-coordinate at all. So sine x equals sine of 90 minus. Sine x equals sine of 180 minus x. While cosine x equals negative cosine of 180 minus x. And as we mentioned earlier, if we shift by pi over 2, that's basically converting from sine to cosine and cosine to sine, all the inverses, as shown in this column. So these are basically the main shifts in trigonometry. And while you definitely don't have to memorize them all, just understanding intuitively how they'll show up on a unit circle is really useful for deriving them. Now we'll move on to some of the other identities in trigonometry. And we'll start with one of the most fundamental of the identity, called the Pythagorean Identity. This basically says that if we have an angle theta, cos squared theta plus sine squared theta equals 1. And this is actually just a direct application of the Pythagorean theorem. Since if you remember from the unit circle, it was centered at the origin, which means that its equation was x squared plus y squared equals 1. And as x equals cos theta and y equals sine theta, this equation holds true for any theta. So this is the one that's used most commonly in competition, but there are also a lot of other formulas that show up occasionally, including double angles, half angles, and sum and difference identities. So each of these, their derivations are rather complicated, so they're generally just ones to memorize. So we have over here the sine of 2 theta equals 2 sine theta cos theta, and cosine of 2 theta equals cos squared theta minus sine squared theta. As a note, cos squared theta just means cos theta times cos theta, but for notation purposes, we put the squared in the inside, so it's different from cosine of theta squared. But if you also notice, there are 3 different ways to write cosine 2 theta, and that's due to this identity of cos squared plus sine squared equals 1. Each of these is just adding or subtracting this cos squared plus sine squared equals 1 from the original equation. And half angles finally are more complex, but they can be derived from these 2 double angle formulas. The actual value, they basically have 2 possible values, which depends on the angle. And the unit circle will help in determining the sign if you know the angle value. They aren't used all that commonly, but knowing them will sometimes be helpful. Finally, we have the angle and sum differences. So there are ways to memorize these using some sort of mnemonic devices again. So if we look at sine of a plus b and sine of a minus b, the signs over here and in the bracket are the exact same. So one common way people used to memorize this is for sine, they have the same sign, but different trig. As over here, you have sine and cosine, cosine and sine. On the other hand, for cosine of sum and differences, the signs are different, as we have a negative over here and a positive over here, and a negative over here and a positive over here. But this time, the trigonometry is the same, as the cosine is paired with cosine and sine with sine. So it's just a useful way to help memorizing how these angle, sum, and addition work. And these are very important as they can be used to derive other angles. For example, let's say we want to find the value of sine of 15 degrees. This isn't something you'd normally have memorized, but you do know 2 other angles that are very easy to memorize. Sine 15 degrees is actually equal to sine of 45 degrees minus 30 degrees, which means we can expand it using the sine of a minus b. So it's just equal to sine of 45 times cosine of 30 minus cosine of 45 times sine of 30. So using the values that we derived last time, this is equal to root 2 over 2 times root 3 over 2 minus root 2 over 2 times 1/2. And if you expand this all out, it turns into root 6 minus root 2 divided by 4. So this value is obviously not something that you're expected to memorize, but if you know these formulas, you can easily derive them when needed. Finally, the last few things that we're going to cover are law of cosines and law of cosines. So these 2 images basically summarize both of them. The law of sines relates the sines of the angles and the lengths of the opposite sides, and says that all the ratios are equal. And on the other hand, the law of cosines is almost an extended Pythagorean theorem. It basically says that if you have any 2 sides and you know the angle in between, you can calculate the third one. And if you used any of these angles as 90 degrees, as cosine of 90 is equal to 0, this would just turn into Pythagorean theorem as expected. Then there's one final thing that we'll do before moving on to competition problems, which involves the area of a triangle. So let's say we take an arbitrary triangle. Let's draw that again. Like this, with angles A, B, C, and side lengths A, B, and C. We could find the area of the triangle if we're given any two of the sides and the angle between it. Specifically, if we draw down this hypotenuse, we notice that since this has measure angle C, the length of this height is just B times sine of C. Since that would be B times opposite over hypotenuse, which is the opposite is this and the hypotenuse is this, so this just cancels out to the length of the height. So using the formula for an area of a triangle of 1/2 times base times height, the area of this triangle is just 1/2 AB sine theta. And we could have done this with any of the three sides. This would also be equal to 1/2 BC sine A or 1/2 AC sine B. And this formula is rather useful when you're dealing with areas and triangles when trigonometry is involved, as one of our later problems will discuss. So now we'll move on to competition problems.
All right, so our first problem, we have that in triangle XYZ, we have that angle X is 90 degrees, and that the tangent of angle Z is equal to 7. It also tells us that YZ, which in this case would be the hypotenuse if we drew out the right triangle, is 100. So then it asks us, what is XY? So like any geometry problem, let's start out by just drawing out this triangle. So we know that X is a right angle and that YZ is 100. So if we draw a right triangle with right angle X, we know that the hypotenuse YZ is 100. So let's label that. And the problem also tells us that the tangent of angle Z is equal to 7. So what we can do is we can let XZ equal to A. And that would mean that XY has to be 7A, since tangent of Z is equal to XY over XZ. So it would be 7A over A, which is 7. So now we have a right triangle with legs A, 7A, and 100. So what we can do now is just use Pythagorean Theorem. What we do is that we have A squared plus 7A squared is equal to 100 squared. So the left-hand side becomes 50A squared. And this is equal to 100 squared. And if we take the square root of both sides, we get that 5 root 2 times A is equal to 100. So that means A is equal to 10 root 2. However, the problem asks us to find XY. So what we actually want to find is what 7A is. So 7A is just 7 times 10 root 2, which is 70 root 2, which is our answer. All right, moving on. Here we have another right triangle question. We have that in right triangle ABC, we have that side AB is equal to 10, BC is equal to 24, and that angle ABC is 90 degrees. So already we know that AB and BC are the two legs of the triangle. So if M is on AC such that BM is the median of the triangle ABC, what is cosine of the angle AMB? So we draw this out. A median is just a line that the median BM with M on AC. So the median is just a line that connects one vertex to the midpoint of the opposite side. So in this case, M would be halfway in between A and C. So that means AM would be half of AC. So a special property of right triangles is that the median is equal to exactly half of the length of the hypotenuse, which means that AM equals BM. And we can see this more clearly if we split up ABC into 4 smaller triangles. If we draw a perpendicular from M to AB and BC, you can see that we now have 4 right triangles that are all similar to ABC, which means they're all congruent to each other since they have equal area. So by congruency, AM equals BM. So knowing that, we now know that triangle ABM is isosceles, where AM equals BM. So that means angle ABM equals angle BAM. So instead of finding the cosine of ABM, instead we could just find the cosine of BAM. And the cosine of BAM, since it is an angle in a right triangle, this is just equal to AB over AC. So to find AC, we can just use Pythagorean Theorem. We have AC equals the square root of 10 squared plus 24 squared. If some of you guys know your Pythagorean triples, you can see this is a 5, 12, 13 triangle. So this is just equal to 2 times 13, which is 26. So that means cosine of angle BAM is equal to 10 over 26, which simplifies into 5 over 13, which is our answer.
All right, now on to our next question. Sorry. Okay, so we have a rhombus. Sorry, one second.
So we have our next problem. A rhombus ABCD with side length 6 is rolled to form a cylinder of volume 6 by taping AB to DC. So this problem again is like we need to use trig, but it's a bit harder because we're imagining this in 3 dimensions. So here we roll up a rhombus to form a cylinder. So what this would look like is a slanted cylinder. Think something like the Leaning Tower of Pisa or like a piece of penne pasta with a circular base. Well, if we drew out the cylinder, we can notice that the height of this cylinder is actually just the same thing as the height of the rhombus. If we were to draw the rhombus. So that means h of the rhombus is equal to h of the cylinder. So to find h, we can actually just use some trig. We know that the side AB, h, and the base form a right triangle. So we know that h should just be equal to AB times sine theta, which is equal to 6 times sine theta. We can see this because it forms a right triangle with hypotenuse equal to one of the side lengths and one angle equal to sine angle ABC. So, knowing this, we can combine this with what we know about the volume of the cylinder. The volume of the cylinder should just be base times height, where the base is just pi r squared. Well, what's the radius of the base? Well, we know that the circumference of the circle should just be equal to one of the side lengths, since we're taping AB to CD. So the circumference is equal to 6, meaning that the radius is equal to 6 over 2 pi, which is simplifies to 3 over pi. So that means pi r squared is equal to 9 over pi squared times pi, which is just 9 over pi. So plugging this in, we get 9 over pi times h is equal to 6. Since it tells us the volume is 6, we know h is 6 sine theta, so we get that 9 over pi times 6 sine theta is equal to 6, which means that sine theta has to equal pi over 9, which would be our answer. All right, so before we dealt a bit with just like cosines and other trigonometric functions in right triangles to find sides or just evaluate the sine of an angle. But here we deal with more of the behavior of the function. So this kind of differentiates trigonometry questions into two fields of thinking. One is more geometric, whereas the other is more algebraic. So here we have the functions. It tells us that sine x and cos x are periodic with least period 2 pi. And what this means, what we call periodic means that it repeats after every certain length of time. So if you look at a graph of sine x, it looks like a squiggle, and the squiggle repeats every 2 pi. And this is what we call the least period. We call it the least period because it's the smallest period with which it repeats. So for example, sine x is also periodic in 4 pi, but we don't really use that. So it asks us to find the least period of the function cos of sine x. Well, at first you might think, oh, this is just a composition of two functions with a period of 2 pi. So we can just say it's 2 pi, right? Well, not quite. Well, going back to some of the identities we learned with shifts and trigonometric shifts, we know that cos of negative x is equal to cos of x. And we also know that sine of pi plus x would equal sine of negative x, or which also equals negative sine of x. So that means if we take cosine of sine of pi plus x, this is just equal to cosine of negative sine of x. And since we're taking cosine of negative of what we were originally taking, this just becomes cosine of sine of x. So that means this function actually repeats every pi, meaning that its least period, instead of being 2 pi, is actually just pi, which would be our final answer. The period is pi. So continuing with like observing how the cosine and sine trigonometric functions behave, here we have that given that a sub k is equal to k times k minus 1 over 2 times cosine of k times k minus 1 over 2 pi, it asks us to find a of 19 plus a of 20 plus all the way to a of 98. So, well, at first this looks really daunting. We have cosine of an algebraic function. How would we deal with this? Well, what we can do is we can realize that k times k minus 1 over 2 is actually always an integer, since these are what we call triangle integers. We went over this in combo as well as arithmetic series. So since k times k minus 1 over 2 is always an integer, that means cosine of k times k minus 1 over 2 pi is actually just equal to cosine of n pi for some n. And if you look at cosine n pi, where n is an integer, it can either be 1 if cosine is even, so cosine of 0 equals cosine of 2 pi equals 1. And it can also be negative 1, so like cosine of 1 pi or cosine of 3 pi. So if it's odd, it's negative 1. So what we get is that this is just a of k is equal to k times k minus 1 over 2. And if it's odd, it's negative, and if it's even, it's positive. So what this looks like is if we write out a few terms, this would look like negative 19 times 18 over 2 plus 20 over 20 times 19 over 2 plus 21 times 20 over 2 minus 22 times 21 over 2 and so on, all the way to 98 times 97 over 2 would be negative, so minus 98 times 97 over 2. So we can see that the signs alternate every 2. We start with a negative, then positive, then positive, then negative, then negative, then positive, and so on. So we can actually just group them together. We can group together terms negative n times n minus 1 over 2 plus n plus 1 times n over 2. And this just becomes 2n times n over 2 but since we are subtracting, this actually just becomes n over 2 times n plus 1 minus n minus 1, which is n over 2 times 2, which is equal to n. So the first pair of fractions, so negative 19 times 18 over 2 plus 20 times 19 over 2 equals 19. The next pair will be 21 times 20 over 2 minus 22 times 21 over 2. So that would be negative 21 and so forth. So this would just be summing alternating odd numbers like 19, negative 21, 23, negative 25, ... all the way until 97. So if we pair these terms up yet again, we get that each pair just sums to negative 2. We would have 19 minus 21 is negative 2, 23 minus 25 is negative 2, and so on. And in total, there are, well, 98 minus 19 plus 1 over 4 such pairs, which is equal to 20. So that means that our sum is equal to negative 2 times 20. And we want to find the absolute value. So this just becomes absolute value of negative 40, which is 40.
All right, moving on to the next question. So this time we're given that the sum of two sines is square root of 5/3, and the sum of two cosines is 1. And we want to find the value of the cosine of their difference. So while the last problem was a good example of how trig questions and that deal with the behaviors of trigonometric functions, there are also questions like this that deal mainly with identities. So to start off, nothing is very obvious, but we can see that the sines and cosines are separate. So we could try adding both sides, but nothing exactly happens. So, but what if we instead square both sides first? We would get that sine squared a plus 2 sine a sine b plus sine squared b equals 5/3. And if we did the other one, we'd get cos squared a plus 2 cos a cos b plus cos squared b equals 1. But now we notice that we have a sine squared a and cos squared a and a sine squared b and a cos squared b. And if you remember the Pythagorean identity, we can add these to get 1. So now if we add both these equations together, this just becomes 1 plus 2 times sine a sine b plus cos a cos b plus another 1 equals 8/3. So that means we can again simplify this. We get that if we notice this inside looks oddly familiar too, and that's because it's the sum of the cosine a minus b. Specifically, cosine of a minus b equals sine a sine b minus plus cos a cos b, which is exactly what we have on the inside, which means you can rewrite this as 2 times cosine of a minus b plus 2 equals 8/3. So if we just simplify this, this basically gives us that cosine of a minus b equals 1/3. Sorry, equals, 1/3, which is basically all that their problem is asking us, which means their answer is just 1/3.
All right, so moving on for our next question. We want to find a positive integer n such that arctan of 1/3 plus arctan of 1/4 plus arctan of 1/5 plus arctan of 1 over n equals pi over 4. So we haven't really discussed arctangent functions or arcs or arc trigonometry trigonometric functions. So a brief explanation is just if you take arcsine of theta, this would just equal theta. So basically it's like the inverse function of sine of x. But this isn't to be confused with something like cosecant theta, since they're completely different concepts. So the arctan of 1/3 would just be the angle that would satisfy tangent of theta equals 1/3, and so on and so forth. So in general, arctangent functions and arcsine functions are just annoying to deal with. They're not really nice functions. So what we want to do is we want to get rid of them. We want to turn them into just good old trigonometric functions, because that's what we know how to work with, right? So since we know that if we take the tangent of an arctan of, like, let's say 1/3, that would just be 1/3. So why don't we just take the tangent of all of the arctans? So we have tangent of arctan 1/3 plus arctan 1/4 plus arctan 1/5 plus arctan 1 over n equals tangent of pi over 4. Well, now we can see this actually looks just like the sum of angles in a tangent. So our formula for sum of angles in a tangent is just the formula we have for sum of angles in tangent is tan A plus tan B over 1 minus tan A times tan B. So in this case, where A and B are both arctangents, things actually cancel out very nicely because tangent, so let's say we do the first two terms in our sum first. Well, these two would just become tangent of arctan of 1/3, which is 1/3, then tangent of arctan of 1/4, which is 1/4, over 1 minus their product, which is 1 minus 1/12, which gives us which gives us 7 over 11. Now, if you continue this, well, we can turn this back into an arctan. So our new sum becomes tangent of arctan of 7 over 11 plus arctan of 1/5 plus arctan of 1 over n. And this should equal tangent of pi over 4. So if you continue this, well, we can do the same thing with our next pair of numbers, 7/11 and 1/5. So we have 7/11 plus 1/5 over 1 minus their product. And this yields us 23 over 24. So now all we have left are arctan of 23/24 and arctan of 1 over n. And we know that the tangent of these should be equal to tangent of pi over 4, which is 1. So thus, we can use our final sum of angles. We have 23 over 24 plus 1 over n minus over 1 minus their product, so 23 over 24n. And this is equal to 1. So simplifying this, we get, if we multiply both sides, we get 23n plus 24 equals 24n minus 23. Solving for n, we get that n is equal to 47. All right, so here we've dealt with trigonometric identities in very algebraic-based questions where we had to use algebraic manipulation. But here is an example of using trigonometric identities in a more geometric problem. So here we have triangle ABC. The tangent of angle CAB equals 22/7. And the altitude from A divides BC into two segments of length 3 and 17. And it asks us to find the area of the whole triangle. So if we were to draw this out, like always with a geometric question, we have, let's say the top is A, then we have C, and then B. So we draw the altitude. We can split CB into 3 and 17. So at first, we might not really be sure what to do. It's not immediately obvious, but, well, we know that D is the intersection of altitude with BC. So let's call H the length AD and D the base of the perpendicular. So we know that BD is equal to 17 and CD is equal to 3. We also know that tangent of CAB is equal to the given, which was 22/7. So we know that. So we can also figure out tangent of BAD. Or tangent of BAD, well, since ADB is a right triangle, since AD is perpendicular to BC, we have tangent of the angle BAD is 17/h. And we do the same with angle CAD. We get tangent of CAD is 3/h. So what we can do now is, well, we know tangents of BAD, CAD, and CAB. We can just write a equation out with the sum of tangents. We know that tangent of CAB is equal to the tangent of DAB plus the tangent of the tangent of DAB plus CAD. So expanding this, we get 22/7 equals tangent of DAB plus tangent of CAD over 1 minus their product. So we get that 22/7 equals 17/h plus 3/h over 1 minus 17 times 3/h squared, which simplifies to 20/h over 1 minus 51/h squared. If you multiply both the numerator and the denominator by h squared, this becomes 20h/h squared minus 51. So then now we can cross multiply and we move all the terms to one side, and what we get is the quadratic 22h squared minus 140h minus 22 times 51. And with a little bit of testing, we can figure out that this factors into 2 times 11h plus 51 times h minus 11. Since h has to be positive, that means the solution for h is 11. So now we know the height is 11. We know the base is just 3 plus 17, which is 20. So that means the area is 1/2 base times height, which is 1/2 11 times 20, which is 110, which is our answer. All right, so here we have another geometric trig question. So we have a rectangle ABCD. So let's draw those out. We know that AB equals 20 and BC equals 10. So AB is the longer side. So let these be A, B, C, and D. So point E is on CD, such that the angle CBE is 15 degrees. And it asks us to find the length of segment AE. So let's draw that in too. Now, well, we only know one angle, so let's put that to use. So, well, we know one angle, we know one side, and we can also see that triangle BCE is right triangled. So why don't we try finding the tangent of 15? That way we can figure out EC, because we can write EC over CB equal to tangent of 15 degrees. Since BC is equal to 10, we get that EC equals 10 tangent of 15 degrees. Well, how do we find tangent of 15 degrees? Well, we can just use our tangent half angle theorem. So if you remember our tangent half angle theorem, this is equal to the square root of 1 minus cos theta over 1 plus cos theta. And in this case, it will be positive because we're dealing with acute angles. So, well, this seems a bit messy to plug it in because, well, cosine of theta would be 30 degrees, which would be root 3 over 3. So that's not too nice. So what we can actually do is we can simplify this. We can multiply both the top and the bottom by 1 minus root 3 over 3, or 1 minus cosine theta. And we can see that the numerator inside the square root becomes 1 minus cos theta squared, and the denominator becomes 1 minus cos squared theta. And the bottom becomes that because of difference of squares. And if you remember from our Pythagorean identities, 1 minus cos squared theta is just sine squared theta. So now everything inside our radical is a perfect square, which is really nice because that means we can just simplify this into 1 minus cosine theta over sine theta. And this is another handy identity for the tangent half angle. And this is the easier one for me to remember since remembering all the radicals is pretty messy. So now plugging in theta equals 30 to find tangent of 15, we get, well, 1 minus cosine of 30 would be root 3 over 2. And sine theta would be 1/2. So this would be equal to 2 minus root 3. So that means if we plug this in, we get EC equals 10 times 2 minus root 3, which is 20 minus 10 root 3. And conveniently, this cancels out really nice because, well, we know that side AB is 20, so that means also CD is also 20. So that means the length of DE is equal to CD minus EC. So that means DE has to be equal to 10 root 3. So it actually cancels out really nicely. So now, well, we know what DE is. We also know what AD is actually because the problem gives us to us. We know that AD is 10. So if we write these in, well, we can obviously see angle ADE is a right angle since it's a rectangle. Well, now we have a right triangle. We know both of its legs, and we're trying to find its hypotenuse. So we can actually see that this is a 30, 60, 90 triangle since we have a 1, a 10, and a 10 root 3 as the legs. So that means the hypotenuse is just 20. And that is our final answer. So our next question, we have that in triangle ABC, angle ABC is equal to 45 degrees. Point D is on BC such that QBD equals CD and angle DAB equals 15 degrees. So like always, let's start out by drawing a diagram based on what we know. So we know that ABC is equal to 45 degrees and point D is on BC such that 2BD equals CD. So let's say BD is equal to 1 and CD is equal to 2. And this doesn't really change anything because we're trying to find an angle and we can just scale this up and down based on similarity and the angles won't change. So we can assume that BD is equal to 1 and DC is equal to 2. So, well, we're able to find that if you look at angle ADC, we can see that ADC is actually equal to 60. And we can do this through, since we know that angle AC, or we know that angle DAB is equal to 15, and we know that angle B or ABD is equal to 45. Well, that means in triangle ABD, the sum has to be equal to 180. So that means angle ADB is equal to 120, and angle ADC is its complement, which is 180 minus 120, which is equal to 60. So knowing that, we can now use the law of sines on triangle AB. So, well, we know that BD is equal to 1. So we get 1 over sine of 15 degrees equals AD over sine of 45 degrees equals AB over sine of 120 degrees. If you remember from earlier, we know that sine 15 degrees is equal to root 6 minus root 2 over 4. You can always derive this using the difference formula. So sine of 60 minus 45 is equal to sine of 60 times cosine of 45 minus cosine 60 sine of 45, and that gives us root 6 minus root 2 over 4. We know that sine 45 is obviously root 2 over 2, and we know that sine of 120 is equal to root 3 over 2. So that means we can compute that AD is equal to 1 plus root 3, and that AB is 3 root 2 plus root 6 over 2. So now we know all these sides. We can next apply the law of cosines to the triangle ADC. We get that AC squared is equal to AD squared plus DC squared minus 2 times their product times sine or cosine of 60. Well, we know that AD is equal to 1 plus root 3 as we found earlier. And we know that DC is equal to 12 based on our assumptions, or equal to 2 based on our assumptions. We get that AC squared equals 1 plus root 3 quantity squared plus 2 squared minus 2 times 1 plus root 3 times 2 times cosine of 60. Cosine of 60 is equal to 1/2. So simplifying, this becomes AC squared equals 6. So now that we get that AC squared is equal to 6, and this is because if you expand it out, you would get 1 plus 3 plus 2 root 3 plus 4 minus 2 root 3, which is equal to 6. The root 3's cancel out. We get that AC is equal to square root of 6. So now we can yet again apply the law of sines to triangle, but this time we can apply to the larger triangle ABC. We get that root 6 over sine 45 is equal to 3 root 2 plus root 6 over 2, which is what we got AB to be, over sine ACB. So plugging in that sine 45 equals root 2 over 2, we get that ACB equals root 6 plus 3 root 2 over 4 root 3. So if we simplify this a bit, if we divide the top and bottom by root 3, we get that this is actually equal to root 6 plus root 2 over 4. And this is actually very similar to the form of what we got sine 15 to be. So except we're changing a plus or a minus. And if you toy around, you can actually figure out that this is either equal to sine of 75 or sine of 105. And you can do this based on the sum to product, or not the sum to product. You can do this based on the sum of angles formula we had earlier. Well, since the angles have to be acute, it can't be 105. So we get that angle ACB is equal to 75. So this is a pretty hefty problem. As you can tell, we spent a lot of time using a lot of trig, and this is what we call a trigonometric bash. It usually relies on like law of sines and law of cosines and their repeated use. And although you usually get the right answer, it's easy to mess up in the middle and it takes a while. So usually it's not always the nicest solution, but it is very consistent. And if you can't figure out any other way to do it, you should rely on this. So moving on, we have that the diagonals in a rectangle PQRS intersect at point X. If PS equals 6 and RS equals 8, it asks us what is the sine of angle PXS. So we label the points, we have P, Q, R, S, and X in the middle. So we want to find PXS. So, well, the first thing to note is, well, obviously you see that you have 6 and 8, so that means obviously the diagonal is going to be 10 since it's a rectangle. You have 6 squared plus 8 squared, the square root. So PR is equal to 10, but that also means that PX, SX, RX, and QX, which are all half of the diagonals, are equal to 5. So we get PX and SX are equal to 5. So you can actually figure out all the sides of triangle PXS. It has side lengths 5, 5, and 6. But we also know that if you look at angle PSX, the sine of PSX well, the sine of PSX is just the same as the sine of angle S. And if you look at the triangle, the right triangle, PSQ, you get sine of S is equal to 8 over 5, which is 4/5. So you get sine of PSX is equal to 8, or equal to 4/5. So here, we can just use the law of sines. We know the side lengths of a triangle, we know one of the sides, and we want to find another. So we get that, well, 5 over sine PSX equals 6 over sine PXS. And make sure when you use the law of sines, you use the right sides. It's easy to sometimes get mixed up if you're too far into a problem. So if we simplify this, we get sine of PXS is equal to 6 over 5 times sine of PSX. Substituting in PSX, or sine of PSX equals 4/5, we get that sine of PXS is equal to 6/5 times 4/5, which is 24 over 25. And that is our final answer. So for our next question, and also our last question, we have that in triangle ABC, the product of the sines of all three angles, so sine A, sine B, sine C, is equal to 1/1000th. And we know that ABC, or AB times BC times CA, so the product of all three sides is equal to 1000. And that's just for the area of a triangle. Well, at first you might be like, well, you're not giving us enough information. We know what the products are, but we don't know what the sides are, what the angles are. But, well, let's focus on what we're trying to find first. Well, we're trying to find the area of the triangle of ABC. Well, what formulas do we know that give us the area of ABC? Well, we know that area equals 1/2 base times height. We know that area also equals 1/2 AB sine C. We know that area, we can even use Heron's formula, which we've mentioned earlier a bit. But I think if you look at this problem and you look at all the formulas you know based on the area of a triangle, well, there's one that obviously sticks out. 1 times AB, 1/2 times AB sine C. And that's because you have, well, the product of the side lengths times one of the sines. And in the problem, it gives you the product of all 3 sides and the product of all of the cosines, or all of the sines. So, well, if you look at our formula for area, we know that this is equal to area, but this is also interchangeable for any of the sides. So it's the same for 1/2 BC sine A. It's also 1/2 AC sine B. And here we see, well, all of these include all of our givens. We have sine A, sine B, sine C. We have side A, which side B, side C. So if we actually just took the product of all 3 of these, you get that the area cubed is equal to, well, first 1/8, since all the 1/2s. Then you get A squared, B squared, C squared, times sine A, sine B, sine C. And in this case, well, if we didn't clarify earlier, like the uncapitalized A would refer to side BC, the uncapitalized B would refer to side CA, and so on. So this is just, well, this just becomes 1/8 times, well, 1,000 squared, since it's the product of the 3 sides squared. And then this would just be 1 over 1,000. So we get that the area cubed is equal to 1,000 over 8, which is 125. So that means that our area is equal to cube root of 125, which is just 5. So that's all we have for today. I guess a quick recap is just for trigonometry, there are a lot of tools you can use, like law of sines, law of cosines. You have like the formula for an area of a triangle. You have a host of different trigonometric identities you can use. I guess with trigonometric questions, it's just like getting to know when you have to use which identities or which formulas. And we'll be posting homework for some more practice on that later. If you want to check it out, it should be open a few minutes after the meeting. I guess that's all for today. This is our second last meeting, so I hope to see you guys next week in our last meeting. And yeah, thank you.